All right, to kick off the new set of material, we're going to start by looking at cylindrical and spherical coordinates, which can be found in chapters, or rather sections 15.8 for cylindrical coordinates and chapter 15 or section 15.9 for spherical coordinates. Those sections also introduce some higher level triple integrals that we'll be looking at quite a bit later, but for now we're just going to look at the coordinate systems. So if we check out our learning objectives this time, just the one will translate in between three sets of coordinate systems for 3 space, those being rectangular, cylindrical, and spherical coordinates, where rectangular is already the one we've been working with, and cylindrical and spherical coordinates will both be a 3-dimensional extension of polar coordinates. So here in the learning objectives box, we've got a quick review of polar coordinates, which is where we change x and y into r and theta. So we parameterize both x and y using 2 new variables, r and theta, r being the distance in the plane from the origin, and theta being the angle between the x-axis and the line that connects the origin to our point. So we'll look at 2 extensions of that polar coordinate system into 3 space, the first of which will be cylindrical coordinates. And in cylindrical coordinates, we're going to pretty much keep polar coordinates exactly the same and just add the z coordinate onto the end. We'll just tack that on. So it will still just be polar coordinates in the xy plane, but also there's a z coordinate. So we'll have r, theta, and z being that triple, where r and theta, again, are just polar coordinates in the xy plane. Z is the usual z coordinate. So nothing too fancy there. If we look at a series of equations to help us convert in between the two, if we're going from cylindrical to rectangular, we'll use the same 2 equations we had for polar coordinates, where x is r cosine theta and y is r sine theta, and z will just be z. So nothing to change there. And going from rectangular to cylindrical coordinates, we'll want to use a couple of equations, but also they should be familiar from polar coordinates. R squared is equal to x squared plus y squared. It's basically the Pythagorean theorem. And tangent theta is equal to y over x. Since if we construct a triangle made out of y and x, and then theta is the angle that's inside that right triangle, y should be our opposite side while x is our adjacent side. One quick note is to be careful with the tangent inverse function. For example, the range of tangent inverse of, how about, let's just put t in there. The range of tangent inverse of t is always going to be negative pi over 2 to positive pi over 2, non-inclusively, because tangent of pi over 2 and tangent of negative pi over 2 are both undefined. But if we use the tangent inverse function and we're in the first quadrant, everything works out totally fine. But if we're outside the first quadrant, things tend to get a little more complicated. So you may want to review the tangent inverse function if you plan on using it in the future, which probably there will be some examples where you'll need the inverse tangent function. Another quick note is that tangent inverse is also arctangent. Just another name for it. But they mean the same thing. Tangent inverse and arctangent are the same function. So let's take a look at where all those pieces are coming from. So if we have our point, check out our point, it's right there. And it's some point out in 3 space. It is somewhere above the xy plane. And we're looking to convert that point, which is in xyz, into cylindrical coordinates. Then how are we going to go about doing that? Well, I've already labeled r and theta on here for us, so that r is the distance from the origin to the projection of our point into the xy plane. that being this guy down here is that projection, and r is the distance from the origin to that point. And theta then is still the angle from the x-axis up to our line r. And if we take a look at this right triangle right here, we can find equations for x and y. So in that triangle, x is the adjacent side while r is the hypotenuse, which gives us the equation x equals r cosine theta, just like we would have in polar coordinates. Same thing, if we continue looking at that highlighted green triangle, then we get that y is equal to r sine theta, since y is the opposite side of that triangle, and r, of course, is still the hypotenuse. And we said that for cylindrical coordinates, all we want to do is just extend this system straight up, so that the z-coordinate will still be the z-coordinate. So z doesn't change between polar coordinates and rectangular, or between cylindrical coordinates and rectangular coordinates. And that's the system. We'll look at a couple of just examples of what some basic shapes look like in cylindrical coordinates. If we have the function r equals a constant number, that's going to be a cylinder. Whereas in polar coordinates, r equals a constant number is just a circle with a radius of whatever that number is. So r equals c would be the radius. But now it's a cylinder because the z coordinate lets it extend up and down. And if we have the equation z equals r, we end up with the equation for a cone. Since if we were to, or yeah, let's leave it right there. Z equals r is a cone. All right, let's convert between those two coordinate systems. So describing the surface, z equals 2 minus 4r squared. So from section 12.6, we looked at several ways of describing quadratic surfaces, quadratic surfaces. So we're going to want to do the same thing here. And in order to do that, we'll convert this cylindrical equation back into rectangular coordinates and see what we have. So for starters, we'll have z equals 2 minus 4 times r, or well, r squared, we know is x squared plus y squared. So we'll substitute that in real quick, which gives us the equation z equals 2 minus 4x squared minus 4y squared. And we want to describe what that surface looks like. So based on the stuff we had in section, what was that, 12.6, the quadratic surface section, we have an equation that has one first order term being z and two second order terms, so two square terms, x squared and y squared. So since we've got that first order term, we know we should have some kind of a parabolic surface, which is what happens if we mix first and second order terms together. So some parabolic shape will be in here, and then both of our square terms have the same sign. If the square terms have the same sign, we should have some sort of an elliptical part to our surface as well. So putting those together, this must be an elliptical paraboloid. Elliptical paraboloid. Right. Then on to the second part of the example, rewriting the surface z equals y squared minus x squared, this time in cylindrical coordinates. So that should give us the equation z equals, that is r sine theta is y, so r sine theta squared minus x, which is r cosine theta, and then squared, will allow us to simplify this thing to r squared times sine squared of theta minus cosine squared of theta, which it would probably be fine to leave it right there, but that is an identity. If we remember our trigonometry, this will be equal to negative r squared sine of 2 theta. Oop, that's not quite right. That's negative r squared cosine of 2 theta. Where we get that from the double angle formula. So if that is completely unfamiliar to you, it's not a big deal, but I would recommend reviewing the double angle formula, as we will end up needing to use it quite a bit later on. And the double angle formula for cosine has 3 different forms, and we may end up needing to use any one of those 3. So check out the double angle formula if that is unfamiliar to you or if you just forgot all about it. All right, then let's move on to spherical coordinates, where spherical coordinates will be the triple given by rho theta phi instead of x, y, z or r theta z, where rho is the distance from the origin, theta is the same as it is in cylindrical and in polar coordinates, and phi, the new angle, is going to be the angle between our line for rho and the z-axis. So if we look over to the figure on the right, we can see phi is labeled there right next to the z-axis, going out to our line for rho, and then theta, again, is just the same as it is. So 2 new Greek letters got thrown into spherical coordinates, so now all 3 coordinates are Greek letters. The first one is rho, and it's that thing that looks like a P, but it is Greek for R, so that's why it's rho. We just turn R into its Greek component, that being rho. So labeled there, it's pronounced rho, and then if you're trying to spell it, I believe it's RHO. And we'll look at a couple of restrictions on our 2 new variables just to make the system work a little bit easier. So this isn't always true, just working with these restrictions makes it a bit simplified. So we'll look at rho always being a positive number. That we could have, we can have a negative rho value. It just means we would go backwards through the origin instead of forwards. But for simplicity's sake, we'll just look at positive rho values or 0. And we'll also restrict phi to going between just 0 and 1 pi. So for theta, we usually let that go between 0 and 2 pi, since that lets us go all the way around the circle, which lets us complete the entire xy plane. But since theta is already going around a full circle, we're only going to need phi, the one that connects to the z-axis, to go through half a circle. So that in angle phi is equal to 0, that means going straight up the z-axis. And if phi is equal to pi, that means we're going straight down the z-axis. And then any angle in between 0 and pi will let us hit any angle that we need in between the top and the bottom z-axis. So we'll just let phi exist between 0 and pi, again, for simplicity's sake. Since if we went beyond pi, we could just rewrite our equation to have one of phi's reference angles to make it come together a little bit nicer. Okay, and then converting between spherical and rectangular coordinates, we have some equations that are relatively similar to the cylindrical coordinate equations. So we still have x being related to cosine of theta and y being related to sine of theta, and z does not depend on theta at all, just like it did in cylindrical coordinates. But now each of our points in spherical coordinates are going to depend on phi. So we'll see that phi shows up in all 3 coordinates, all 3 components. And if we're going from rectangular to spherical coordinates, then we have another set of equations where we'll just extend r squared to be rho squared is x squared plus y squared plus z squared. Tangent theta is still the same, it's y over x. And for phi, we'll define it using cosine of phi is equal to z over rho. And if we expand on that and look at where all these pieces are coming from, same point we looked at for cylindrical coordinates, but now we're going to turn it into spherical coordinates. So theta in green, that's still the same. I've put r back in, it just being the distance from the z-axis to our point, straight line distance from the z-axis to our point, or from the origin to the projection of our point in the xy plane. But this time it's just going to be a little bit, it will be simpler to look at it as the distance from the z-axis to our point, so that we can take a look at this right triangle that exists right next to the z-axis. And if we take a look at that right triangle, its hypotenuse is rho, the opposite side is r, and the adjacent side is z, which gives us the equation first that sine of phi is equal to r over rho to relate cylindrical coordinates to spherical coordinates. And then we'll use that substitution that r is equal to rho sine phi to change from cylindrical into spherical and see where all these equations come from. So up at the top, I've got our cylindrical coordinates written down again. So x is r cosine theta. And if we want to extend that into spherical coordinates, we'll just replace r, which is a cylindrical coordinate, with rho and phi, which are the spherical coordinates. So r is equal to rho sine phi, which is where the rho sine phi comes from in the x equation of spherical coordinates, and then still multiplied by cosine theta. We can do the same thing for y, where y should be rho sine phi, and then times sine theta. And then finally z, if we come back to that highlighted triangle, z should be rho cosine theta, since z is the adjacent side in that triangle. So we've got rho cosine phi. And there we have it. Those are the cylindrical coordinates. All right, after that, we look at a few basic shapes in spherical coordinates. So spherical coordinates get its name because it's very easy to represent spheres in spherical coordinates, just like cylinders are very easy in cylindrical coordinates. Circles are very easy in polar coordinates. We just extend that a little bit further. But some basic shapes. We've got rho equals c, that's a sphere. Figure 3, if theta equals some constant number, then that's a half plane, assuming again that we're only fixing rho to be a positive value. So rho will only extend in the forward direction along our angle theta. And then in figure 4, we look at the equation phi equals a constant number, so that angle phi. And this time it'll come up with a half cone again under the restriction that we're only letting rho be positive. Positive or zero, I should say. So if phi is equal to an angle in the first quadrant, we have a cone that goes up the z-axis. And if phi is equal to an angle in the second quadrant, then our cone goes down the z-axis. And one more example, converting this time between spherical and rectangular coordinates, describing the surface rho equals 4 cosine theta sine phi. So I'm going to start by multiplying both sides of that equation by rho. Since anytime we've got a rho by itself, it's usually easiest to multiply the entire thing by rho. So doing so gives us rho squared equals 4 rho cosine theta sine phi. And I'm just going to reorder those terms so that they match the one that we had earlier, or the setup that we described above. So I just switched the order there, so we can see right away that if we have rho sine phi cosine theta, that is one of the coordinates that we looked at. So that on the left, rho squared is going to be x squared plus y squared plus z squared. So those two pieces come together. And on the right, rho sine phi cosine theta, that's equal to x. So this is 4x. We just put those two pieces together. All right, so now we want to talk about what kind of a surface this thing is. And this looks like a circle that we should be, or this has a square that we can complete. So what we'll do, take x squared, subtract 4x to the other side. I'll leave a small gap here, plus y squared plus z squared equals 0 on the other side. But then I want to complete the square on x. So if I've got x squared minus 4x, the completed square means I need to add 4 to have a square that's completable. And if I add 4 to the left side, I also add 4 to the right side, meaning that I get x minus 2 squared plus y squared plus z squared equals 2 squared. So in the end, the shape that we're looking at here, this is a sphere, since I've got the equation for a sphere. A sphere with a radius of 2 and a center of 2, 0, 0. So it's moved 2 units along the x-axis, and then a radius of 2. Going to the other side, we've got a surface, 2x squared plus 3z squared equals 3. We want to rewrite that into spherical coordinates. So this thing should look like 2 times x, be rho squared sine phi squared cosine theta squared plus 3 times z, which is rho squared cosine phi squared. And that's equal to 3. And we'll see if there's any simplification to be done here, but it doesn't really look like it. Well, it looks like we can at least factor a rho squared out of everything, leaving 2 sine squared phi, sine squared phi, cosine squared theta, color-coded again so we can keep our angles straight, plus 3 cosine squared phi equals 3. And there's not much simplification to be done here. So I think we'll leave it right there.